us now discuss the space vector PWM generation by analog implementation. This would imply that we will be using op-amps. Just like in the case of the discrete, the principle remains the same. Instead of compare registers, we will use op-amp as comparators, and instead of timers, we will be using a triangle wave generator. Consider a triangular carrier like this of period Ts. And then from this triangular carrier, I will generate another triangular carrier which is slightly offset in this fashion. Reason will become clear shortly, and let us say that I am now comparing this with some modulating signal Vc. Let me now drop the intersection points, drop down the intersection points of the modulating signal with respect to each of the carrier. The blue, the top carrier, and the green, the bottom carrier, the intersection points are like this. I am dropping them down. And let me have two axes, time axis, both are time axis. And let's say one is representing for the top switch and the other is representing for the bottom switch of one arm of an inverter. So let us say this is the A arm of the inverter, this is the top switch and the bottom switch. So let us say for the top switch I will give something like this, a comparator plus minus like this, and let's say if I am calling this as Vc, I will give Vc to the positive, and to the negative pin I will give the blue triangular carrier in this fashion. Now what is the output which is supposed to go to the top switch? Call that as EA. Now whenever the Vc is greater than the triangular carrier, it will be high. So Vc is greater than blue triangular carrier, it is high. You see the intersection point, the blue is here, it will go down and then again come up at this point and then go down here, come up in this fashion. Now for the bottom switch I will use another comparator like this, and now I will give for the minus Vc, and for the plus I will give that green triangular carrier, the one which is offset down. So if that was A, this will be A bar. So now A bar. So whenever the triangle is higher than Vc, it will be positive. So you see here the intersection points, it will be positive at this, in this fashion, like this. So now you see the beautiful aspect of this is that during the transition, this is not a direct 180-degree inversion. As I was saying before, you have to give a dead time. When this is transiting down from on to off, and this is transiting from off to on, there is a period called the dead time. Likewise, when this is transiting from high to low and this is from low to high, there is a period where there is a dead time and both are off. This is called the dead time, so that the top and bottom switches are given enough time for changing the state, because they are having finite rise and fall times. They are practical switches. So this is called this time interval is called the dead time. You include the dead time in the analog case by this manner, by introducing a small offset between two carriers of the same frequency, whereas in the discrete case, you include this dead time by having a small low bit count counter and introduce this dead time by adjusting the count value of that. This would in principle be the way it is implemented in analog. There is one more small item that you need to include, which is injecting third harmonic, triplet harmonic. Why and how, I will tell that. So let us say this is done for each of the each of the arms, that is you have 3 arms for the 3 phase. Let me just show this implementation first in ngSpice schematic, and then I will come back to the modification that we need to do on this. So you see here the schematic in GShem svpwm.sch, and within the page boundary I have the circuit, and outside the page boundaries I have some portions of the circuit like the sources, the DC power supplies, and some filter here outside. These are actually not part of the PWM circuit, because if I have to make a PCB out of it, I need to use only what is inside the page and then put connectors to wherever these items attach. So I have put all these external components for simulation purposes, and what is there inside can be directly sent for making PCB. Okay. Now these op amps, the symbols of them and the models of these op amps are in edt01.sub. The symbols I have already provided for you in my earlier resource. Now I will explain this part. For now, this internal square block, forget it. Let us just see the triangle and comparison. Now this portion is the triangle generator. So it is nothing but, if I expand that, zoom in. So I have an op amp here. This is nothing but an integrator, and the output of the integrator is compared, it's a hysteresis comparator. So let us say at a given point in time when this goes high, this starts integrating down. Because of the capacitor, this will discharge, and this voltage is going down, and as it is going down, once it crosses the whatever the hysteresis lower trip point limit, this will go low, and again this will start rising because there is a change in the state here. Now the current flows and charges up this capacitance, and this will rise, and then again if it goes above the upper trip point, this will change state, so on. So you will get here at this point a triangle waveform. You can simulate and then check that out. Then next, what I do is I am introducing this offset shift. I am using this triangle and adding. Now let us say there is a resistor divider network here, another resistor divider network here. I am making the attenuation point not 10K, 10K. One is 10.1K in one case. The upper resistor is 10.1K. In this case, the lower resistor is 10.1K. So this will be slightly higher value, and this will be slightly lower value compared to 0, because this is positive and negative. And the higher and the lower values I am going to add to this triangle. So one of the adder, I will take this triangle and add it to this offset. I will get one triangle, let's say blue. Then to the other one I will add the other offset, and I will get the lower triangle. So these two triangles will be having a slight offset between them, and that is what we want to use for comparison. So then after that I use a set of comparator. We need two comparators for each arm. So arm1, arm2, arm3. So like that. So for the A phase, the B phase, and the C phase. So I am having top switch, bottom switch. So for one you will use triangle up, for the other you will use triangle low. Triangle up, triangle low, triangle up, triangle low, just like I have discussed. So with hysteresis you will get your PWM at the outputs, which you will give for the top, bottom, top, bottom, top, bottom, like that for each of the arms. So this is the basic working. Now in a normal PWM, this is fine. Sinusoidal PWM, this is fine. But in a space vector PWM, a third harmonic is injected. Now why is a third harmonic injected? Consider this timeline and signal. I have this time. Now I have this extreme limits. This is 100% modulation. These two limits are indicating 100. A sign just touching this line will give you 100% modulation. Now let us say I have a sign like this. It is shooting over the more than 100%. Can I modulate this? You will see that once this 100% modulation reached, it is no longer, it goes to over modulation. It is no longer a linear and a proper wave PWM will not be obtained. Now what we can do is, now let us say I have this third harmonic. Okay, this is the third harmonic triplen, and I will use this. I will subtract this from this. So if a triplen is injected in a three-phase system, it is not going to affect because it is not providing a rotating phasor. And therefore, when I subtract it, you will see that the top portion gets down subtracted because of this. So you will see that the wave shape takes a shape something like that. So you will see that this is just within the 100% modulation. Now this triplen compensated wave shape, the red one, if I use as a modulating signal, then it contains within it a fundamental which is more than 100%, and therefore I am able to get more than this 100% modulation possibility if I inject triplen. So in space vector modulation we use this technique of trying to get more fundamental out of it. A normal sinusoidal will give you just about 100%, and whereas space vector PWM, because of this, can give up to 114%. So that is the extra mileage that you can get. So that is why a third harmonic is added. So coming back to our schematic, this portion of the circuit is how to add that third harmonic component. So here the carrier is this triangle generator here, and the modulating signals VA star, VB star, VC star are coming from here. Now one can add the triplen third harmonic to the input reference wave shapes themselves and then use it for modulating, or you can add the correction to the carrier itself and then not add any corrections to the input reference wave shapes. It is easier to add correction at single point, that is, instead of adding correction to every all three phases, you can add the correction to just the carrier and then get the same effect. So the idea is like this. You have this three-phase reference wave shapes, VA star, VB star, VC star, which is in between the modulating extremes. Now let me remove the color and then remove all the in-between lines. I am just now marking the envelope. So we can correct the by including the triplen, because we have to get a triplen. From where can you get the triplen? From the reference itself. So use the reference. This envelope is containing third harmonics because it's a three-phase system. After correction, the carrier should follow in this fashion, go up and down in this fashion. So after you add to the carrier the triplen harmonic. So how do you do that is, let me mark off these portions. So this portion can be removed, these portions, if you see, and if I call that envelope as X and the bottom envelope as Y, and if you say see X minus Y, you will get something like that. This is a third harmonic signal. So this third harmonic signal can be added to the carrier. So normally the half of that value is added to emulate the space vector PWM, and this would be the triplen injection, and then you will get exactly similar type of modulation like what we discussed in the discrete case. Let us understand this by going to Octave. I have a small script written svpwm.m. So here what I am trying to do is, what is the effect of third harmonic triplen injection into the fundamental, and what is the advantage you gain again in SVPWM because of the third harmonic. See, in the discrete case, because at the offset we had included minus t min plus t naught by 2, the t naught is the zero space vector case time corresponding to that, and it is not equal on both sides, t naught by 2 and t naught by 2. They are varying by the as the envelope is changing. So there automatically the third harmonic gets into picture, and because of that you get that extra mileage of 14% more fundamental as compared to the regular sinusoidal PWM. So here in the script I have first point is generate the three vectors VA, VB, VC, which is sine 2 pi 50 into t, omega t minus 2 pi by 3, omega t minus 4 pi by 3. So we have the three sine waves. Now let me execute this SVPWM. So I first plot these three sine waves. That's what I am plotting here first. Now you have the 0.866 point up here. Now consider this wave shape. The max of VA, VB, VC would be this envelope, this top envelope here, and the min of VA, VB, VC would be the bottom envelope like this. So you take the top envelope separately, take the bottom envelope, and then take the average of those two. The bottom envelope is having negative values, the top envelope is having positive values. The positive values plus the negative values by 2, and that would be this wave shape. Now this wave shape is actually a third harmonic. You will see that there are 3 peaks within a cycle. So that is a triplen. So I have the triplen here. Now what do I do with this triplen? Let us say I have the fundamental. This fundamental minus this triplen. See, the third harmonic will not contribute to a rotating space vector, because you have this minus 2 pi by 3 minus 4 pi by 3. 3 times if you do, it will become 2 pi, and therefore there is no contribution, there is no phase difference and no contribution to a rotating space vector. So you can safely add triplen harmonic. So to this fundamental I subtract this triplen. What happens? So if I subtract, you see that to each of the original waveform fundamental I subtract this triplen. You see it becomes something like this. The top is flattened out, and then you see that, let us say, the level, the modulation level has come down. So for a fundamental of 1 unit, the modulation required with the triplen injected modulating wave is much lower, let's say 0.86. Now if this modulating wave shape had reached 100%, then the fundamental that you would have gained was much more, 14% more. You would have got 114% fundamental. So now that is the extra mileage that you would get by injecting triplen into the modulating signal and then doing the PWM. So that is why SV PWM, or the space vector PWM, has that extra advantage. Now one can inject this triplen in this fashion as I have done. So I have calculated all the positive envelope by taking the max of VA, VB, VC at any instant, and the bottom envelope T negative I have calculated by taking the minimum of VA, VB, VC vector. Now the triplen I add is take the average of these two, T positive plus negative divided by 2, and that is the triplen wave shape we saw here. This is the triplen wave shape. This I subtract from the original sinusoidal modulating wave shape. What I do, the triplen injected VA would be VA3 is VA minus triplen, VB3 is VB minus triplen, VC3 is VC minus triplen, like this. So now VA3, VB3 and VC3 are containing triplen. And then if you plot that, the triplen wave shapes, you get something like this. So if I plot it alone, you will see that. Let me remove this. Plot T comma VA3, T comma VB triplen, T comma VC3. So you will see a wave shape something like that, with the top flattened out, which gives the extra mileage for the modulation. Now one can subtract the triplen from the original sinusoidal modulating signal, or one can add the triplen to the triangular carrier. Both are fine. So in the analog implementation case, we have added the triplen to the triangular carrier.